Hey everyone, welcome to Snack Time with NASA. I'm your host, Kathleen Gaeta.
And we have engine start. Liftoff from a tropical rainforest to the edge of time itself.
That's like looking through the eye of a needle, and in that tiny space,
we found 10,000 galaxies.
That fusion creates a tremendous amount of energy and is literally what fuels the star and makes the light we see.
We're studying the death of islands that spring forth from volcanism.
In 2135, a potentially hazardous asteroid called Bennu will make a close flyby of Earth. During this encounter, our planet's gravity will tweak Bennu's path, making it a challenge to calculate its future trajectory and the odds of a potential impact late in the 22nd century. Why is this hard to determine? Well, we know how gravity works, but there are still uncertainties in Bennu's trajectory that will be magnified by the close encounter. In addition to gravity, asteroids can be pushed around by non-gravitational forces, like the Yarkovsky effect. When sunlight strikes a rotating asteroid, the day side heats up. As the asteroid turns, the night side cools down and releases the heat. This exerts a small thrust on the asteroid, which can change its direction over time. The Yarkovsky effect is challenging to model, but it can make a big difference in determining where asteroids end up. Because we don't know exactly how the Yarkovsky effect will perturb Bennu's orbit, we have limited knowledge of where Bennu will be as it approaches Earth in 2135. Scientists thus have to consider a range of possible trajectories, depending on how strongly the Yarkovsky effect is pushing on Bennu. A few of these trajectories line up with regions of space called gravitational keyholes. If Bennu were to pass through a keyhole, Earth's gravity would bend its path in just the right way to cause an impact on a subsequent orbit late in the 22nd century. The odds of this actually happening are quite low, but scientists want to know as much as possible. That's one reason why NASA sent the OSIRIS-REx spacecraft to study Bennu from 2018 to 2021. OSIRIS-REx greatly improved our knowledge of Bennu's position, density, thermal inertia, and other properties that can influence how its orbit will evolve over time. The new data allowed scientists to significantly reduce uncertainties in Bennu's predicted orbit, ruling out a number of keyholes for the 2135 flyby and eliminating several future impact scenarios. While Bennu remains a hazardous asteroid, we can now make better models of its orbital evolution thanks to OSIRIS-REx. This will allow us, and our descendants, to better calculate Bennu's risk in the decades and centuries to come.
In order for NASA to map and explore the region around the lunar South Pole, we need to precisely define a system of latitude and longitude on the Moon, including the exact location of the South Pole itself. In the coordinate system adopted by the Lunar Reconnaissance Orbiter mission, the South Pole is here, on the rugged rim of Shackleton Crater. If you stood on this treacherous spot, you'd see the sunlit rim of the crater, encircling a permanently shadowed abyss that's 2.5 miles deep, over twice that of the Grand Canyon, covering an area over 130 square miles. As we return to the lunar surface, three-dimensional maps like this will help guide astronauts to safe landing sites in the challenging landscape of the Moon's South Pole.
Earth Resources Technology Satellite, a new spacecraft attempting to improve the quality of life here on Earth.
From 438 miles above Earth's surface, the newest Landsat satellite will collect data so detailed it can detect both natural and human-caused changes to the landscape. But what really makes Landsat unique is the half-century of data, an unbroken chain of observations over 5 decades. Let's take a look at how we got here. 1966, the U.S. Geological Survey proposes a satellite to study Earth's land masses. But what would that look like? Over the next few years, USGS and NASA researched their options. 1970, NASA gets the green light to build an Earth Resources Technology satellite, an experiment to study and monitor our planet's land surface from space. Launched in '72, this was the first digital data of Earth, repeated at regular intervals with geometric fidelity to allow comparison between observations. This changed how we drew maps, tabulated agricultural production, and assessed damage after disasters. In 1975, NASA launched a second satellite similar to the first. Now they were collecting twice as much data. With Landsat 3 replacing the aging original in '78, focus shifted to the advanced technology planned for the '80s. The Thematic Mapper instrument, launched on Landsat 4 in 1982 and on its twin Landsat 5 in '84, was a major step forward. Collecting 7 different wavelengths, at better ground resolution, and with higher precision, this was the beating heart of the satellite and became the workhorse for a generation of scientists. For the first time, Landsat data had 3 visible bands, red, green, and blue, allowing natural color composite images. With the addition of shortwave infrared wavelengths, the data could better highlight flooded areas, mineral deposits, and burn scars from wildfires. The thermal bands were also upgraded, allowing individual farm fields to be tracked. The 6th Landsat was intended to be another big step forward, but it never reached orbit after launch in 1993. Plans immediately began for Landsat 7, which would carry an even more improved sensor. At the time, the Enhanced Thematic Mapper Plus was the most stable Earth observation instrument ever sent into orbit, and the calibration could be updated while in space. For the first time, we had an instrument robust enough to collect lots of data, and we had a plan to thoroughly record the entire globe. Landsat 7 was put to work mapping coral reefs, and even produced the first high-resolution natural color map of remote Antarctica. Improvements to the thermal bands on Landsat 7 allowed states and counties to gauge how much water was used by crops. This helps them manage water resources efficiently. An important milestone occurred in 2008, when the USGS made the data available to download for free. Users were able to get the data they needed, and not just what they could afford. It really unlocked a ton of innovation and created about $2 billion a year in economic benefits. The modern era of Landsat observations began with the launch of Landsat 8 in 2013. Having a push-broom-style sensor on Landsat 8 was a big improvement over the older scanning sensor. The Landsat 8 ground system that USGS runs is capable of receiving a lot more data than before. We're downloading over 725 scenes each day. That just wasn't remotely possible until Landsat 8. The 2 European Sentinel-2 satellites were designed to mesh with Landsat so that users can treat data from all the satellites as if it came from one single source. Now we get observations every 2 or 3 days, instead of every 2 weeks. 2021 is the launch of Landsat 9, the next step forward. It will collect the best data ever recorded by a Landsat satellite, while still integrating seamlessly with the extensive archive. Since the early 1970s, Landsat satellites have allowed us to better manage our resources. Landsat data has enabled countless innovations and will let us track the effects of climate change into the future.
This is it. I am standing at the place where the beryllium was mined for the James Webb Space Telescope. Let's take a step back. I traveled just south of Salt Lake City to a town called Delta, Utah. Well, here we are. What is it? 5:30 in the morning. And then back on the road the next morning as the sun rose up to meet the beryllium miners, all in my quest to find out. So Utah is home to many valuable materials: copper, magnesium, uranium, gold, and silver. But most of the world's beryllium is mined here. And engineers chose beryllium for Webb's mirrors because it is lightweight, it is strong, and it is dimensionally stable. So that means that it is not going to warp when operating at really, really cold temperatures. What is even here? As we were driving down into the pit, I learned that we were in fact driving on the beryllium. This rock looks nothing like metal. Where is the beryllium? How does this turn into this? I, of course, needed to speak to an expert, and he came in the form of the VP of Operations, Greg Gregory.
So we're actually standing right on top of the beryllium ore seam. Beryllium is in a volcanic ash dust. It was hydrothermally deposited millions of years ago and then covered by volcanic rock. We have to remove the volcanic rock on top of the ore seam, and then we use a scraper and a bulldozer to extract the ore that we're standing on top of. 90% of the beryllium that was mined in the world last year came from this deposit.
Let me clue you into how rare this metal is. This area has most of the world's known beryllium, but the highest concentration is only through a 10-foot tall diagonal ribbon well below the surface of the ground.
The ore concentration is 0.25% beryllium. So that means that in a ton of ore, there's about 5 pounds of beryllium. So to get to this point, we had to remove 400 feet of rock to get to the ore seam.
Once the ore is extracted, it goes through a bunch of processing to extract the pure beryllium. Then the powder beryllium is pressed into a block, ready for machining. Webb's mirrors started out as solid 5-foot tall, 5-foot wide, and 2-inch thick blocks of beryllium. But in order to machine those blocks, millions of pounds of rock were removed. It comes to about 4 tons of rock for every pound of beryllium. That is a lot of work for one remarkable metal. Don't look like that. Not being helpful.
Yeah.
I came up with elements of Webb because I had seen in all of our articles and videos that we kept mentioning that we used gold and beryllium for these mirrors, that there are all these special materials, but we didn't really explain why we used them. So I wanted to get sort of into the nitty-gritty of the material science to explore why these were, and then actually just demonstrate why these materials behave the way that they do.
Not only was it a I think, cool science adventure for you because you did a lot of that research. It was an adventure just going out and capturing everything.
That's the great, beautiful Salt Lake back there. Okay, we just got attacked by, they're still swarming around us, these little gnats.
I will say that my proudest moment was being able to go to the beryllium mine. That took a lot of work to get to. You know, we found the beryllium shop, and then we got them to talk to their people, and then convincing those people to let us, you know, fly into Salt Lake City and actually go to the frickin' beryllium mine.
This has all been mined out, so that's the point.
We've had like so much latitude in this project, which we're very lucky. But yeah, so we were able to hire a drone operator, which was so cool. And so he was able to get perspectives on this huge hole in the ground that we would never otherwise be able to see. And actually get like a really good perspective on like just how massive it is and really how much rock you have to remove to get even the smallest amounts of beryllium.
COVID just wiped this whole thing out because we were planning to go to a lot of different places, and then when COVID hit and we couldn't go anywhere, she did, I want to say, like 80% of the whole production at your house.
Yeah.
And you did some amazing stuff at your house.
We're recording.
But first, I have to make some distilled water. It was fun. I mean, it made me take a little more time to think about what I was talking about, and I actually think they ultimately made a better video.
I already see two pieces.
One of the great things about this job is that you can, you meet a lot of different people, you learn a lot of stuff, but you're also able to go into places and see things that, nobody else gets to see. And I think the Elements series is really one of those projects that we were just able to go and into different places.
Sort of my philosophy on life is just start doing the things that you want to do. You're never going to have the gear that you want. You're never necessarily going to have the time that you want, but like try to figure it out and just do it.
NASA's Fermi Gamma Ray Space Telescope has spotted the shortest burst of gamma rays ever seen from a collapsing star. It challenges the traditional classification of gamma ray bursts, also called GRBs. Short GRBs, those lasting less than 2 seconds, are thought to occur when orbiting objects like neutron stars spiral together and merge. Longer bursts come from massive stars at the ends of their lives. A black hole forms at the center of the collapsing star. It drives long-lasting jets that drill through the star, producing gamma rays when they emerge. The star then transforms into a supernova. On August 26, 2020, Fermi detected a GRB lasting about 1 second. Instruments on other spacecraft saw it too, including NASA's Wind and Mars Odyssey missions. They helped narrow down the location to a patch of sky in the constellation Andromeda. Less than a day after the GRB, astronomers identified a fading source of visible light using the Zwicky Transient Facility at Palomar Observatory. This was the burst's afterglow. NASA's SWIFT satellite soon recorded X-rays from it, and within days, ground-based radio telescopes observed it too. After a few weeks, when the afterglow had decayed, ground-based observatories confirmed the presence of a brightening supernova. This means the GRB must have come from a massive collapsing star, not a merger. Astronomers think this burst, called GRB 2008-26A, was on the verge of not occurring at all. About 6.6 billion years ago, a massive star in a distant galaxy reached the end of its life. Its core collapsed and formed a black hole, which launched near-light-speed particle jets through the star. But just as they breached the surface, the jets shut down, producing a surprisingly brief GRB. Astronomers think it's likely some short GRBs they've detected are misclassified as mergers, when instead they're really bursts from jets that nearly failed to drill through collapsing stars. We only detect GRBs when the jets aim in our direction. Even accounting for this, long GRBs still occur at a lower rate than the supernova type associated with them. This means most collapsing massive stars likely fail to produce long-lived jets, dying, at least from the gamma ray perspective, with a whimper instead of a bang.
So we received samples from the Apollo 17 mission, which were returned to Earth in December of 1972, so nearly 50 years ago.
Basically collected on the moon, brought back, then they were frozen within about a month of being returned, so no one's ever looked at them since. It's very exciting.
A curation facility at NASA Johnson Space Center sent us the samples, and they did have to do some special efforts to keep them cold because we wanted them to stay frozen. So they had a special cold shipping box with panels that were frozen in a very cold freezer and a chunk of dry ice. We picked it up from the receiving office here at Goddard, opened it up, pulled the samples out, and stuck them straight in our freezer and locked them up safely.
So these frozen samples were actually collected from a region on the moon that was in shadow from the sun. So it was basically a large boulder. In the near future, we're going back to the moon and hopefully going to the polar regions of the moon, where some of these regions are in permanent shadow and they don't see the sun, you know, they're cold. These particular samples are really great analogs for what we might expect to see in the polar regions when we go back.
So we actually started last week to process the samples. So the samples we got are basically dirt, lunar dirt, and we basically made moon tea out of them. So moon tea is what we call it when we pull out the soluble compounds from the soil. And so we basically take the lunar sample, seal it up with a torch in a little glass test tube full of water, stick it in an oven overnight and boil it, and we're just pulling out those soluble compounds that we care about, the same way you'd make tea with boiling water at home.
What we're trying to do is answer some questions about the history this sample experienced at the surface of the moon. The surface of the moon is a really hostile environment. You know, it's not like here on Earth where we have this beautiful atmosphere that protects us from the nasties of space. So we have particles from the sun that are continuously hitting the surface of the moon, and we've got galactic cosmic rays that are coming in and penetrating into the surface as well. So they actually create noble gases in these particles. So you can imagine that there's none to begin with, and then as they get exposed to this space environment, they kind of get more and more buildup of noble gases. And our technique is to actually unlock those noble gases from the sample and measure them so we can come up with what we call a cosmic ray exposure age. So it's basically how long this sample has been sat at the surface, being exposed, so basically getting a space tan. Say 50 years ago, this same technique, which is called noble gas mass spectrometry, would probably need anywhere, tens to hundreds of milligrams to do the same thing that we now do with a couple milligrams.
It's really special to be part of this, and particularly because I can look back at the papers and the processes that the curation office and the scientists in the 1970s thought about, and they put so much care into preserving these samples for future science, to making sure that they were going to be at the best conditions, so that as we develop new techniques, we're able to go and look at these samples and get new answers to the science questions that were being asked.
You know, I'm still studying these samples 50 years later from the Apollo mission, the original Apollo missions. And, you know, you don't know what's going to be in another 50 years, but I'm still a part of the Apollo dream of going to the moon and bringing samples back. So the fact that we have Artemis now is amazing. Like, having our own Artemis generation is really exciting. I just can't wait to see people go back to the moon.
There once was a star in a galaxy, it was named the Sun, and thankfully it weaves a solar tapestry, sends particles high and low. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow.
The solar wind charts a course, pulling lines of magnetic force, flowing outwards from the source, throws particles to and fro.
Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow. The earth spun with its iron core, and the solar wind knocks at the door. Magnetosphere screams no more until it must let go.
Once a magnetic line is freed, buckling under the wind stampede, it whips back with tremendous speed, sends particles to the poles.
Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow. The particles speed back here and ricochet through the atmosphere, exciting oxygen and nitrogen there, making those particles glow. On and on the cycle spins, sun and earth are celestial kin, dancing through the solar wind, connected by its flow. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow.
Undressed bok choy. Woo! Okay. Hey everyone, welcome to Snack Time with NASA. I'm your host, Kathleen Gaeta. Now, we've been exploring all the ways that NASA helps get some of your favorite foods onto your plate. And so far, all of those foods have been down here on Earth, obviously. But we're NASA, right? So while we may not be professional chefs, we do know a thing or two about space. That's why today we'll be learning what it takes to grow food 200 miles above our heads on board the International Space Station. And later, we'll hear how the space station helps us monitor the health of plants down here on Earth. So let's get into it. As you can see, I have a nice haul of greens right in front of me. Some romaine lettuce, some bok choy, radishes, microgreens. Now, I got all these ingredients from my local grocery store, but actually every single one of these plants is grown on board the ISS. And here to help explain how that happens is Matt Romine, project scientist at the Kennedy Space Center. Matt, thank you so much for being here. How's it going?
Oh, it's going good. Glad to be here, Kathleen.
Yeah, so you sent me a list of vegetables that you work with, and I'm wondering how you go about choosing which foods to grow up in space.
We have to do a lot of crop screening, and we get able to screen these crops and test them in our grow chambers at Kennedy Space Center that are able to replicate the environmental conditions on the International Space Station, except for microgravity. We're looking for how productive they grow, we're looking for compact morphologies, and crops that are nutritious and flavorful.
Okay, and I have to ask, have you ever grown potatoes in space?
Well, we've been growing crops recently on ISS, the last 5 years or so. We have done potatoes recently, but in the past we've done them on the shuttle program, and we've grown them extensively on the ground at Kennedy Space Center.
I will eat a space potato in my lifetime, I promise you that. Anyways, so you suggested I pick up some bok choy and mustard greens, and I can't say those are typical salad ingredients for myself.
The bok choy is interesting because the crew recently grew and got to eat that on ISS, and they really enjoyed it. They actually found a way to cook it using their food warmer and combining some garlic paste, soy sauce, and a bit of olive oil. The mustard greens are great because they have a lot of strong flavors. And when you're an astronaut on ISS, in microgravity, you have a diminished sense of taste and smell. So they like those bolder flavors to kind of punch through there.
Wow, I did not know that. And now, do you also grow the same plants that you're growing in space down at KSC?
Yeah, when we're growing plants in space on ISS, we also have ground controls at KSC that replicate the exact conditions on ISS, the temperature, the humidity, the CO2 levels. Control for everything but the microgravity element.
Okay, and I assume that's so that you can more closely monitor the difference of plants growing in space versus on Earth. What have you discovered in that process?
Well, we find that plants for the most part grow similar in space as on Earth. A big variable is the water. There's a lack of convective flow in space, and that makes water very sticky. Plants like a good mix of water and oxygen in their root zone, and when we have water that doesn't mix well with oxygen, we get a lot of swinging back and forth between the roots being flooded and being in a state of drought. So we have technologies that are working on that to solve that problem with microgravity. Luckily, when we get to Mars and the Moon, those problems mostly go away.
Got it. And so talk to me about this little space garden I keep hearing of, the veggie growth system. What is that?
Yeah, the veggie, we've got 2 of those in ISS, and it's a real simple system. It's about the size of a piece of carry-on luggage. It uses LED lighting, and it has 6 little plant pillows in them that are filled with growth media, which is basically a soil substitute. And that's how we're able to grow and propagate the plants in ISS.
That's so interesting. The vision of a space garden just brings a lot of joy to me, and I'm sure a lot of people. Anyway, so is there a plant that you're kind of the most excited about trying to grow in space?
Definitely peppers. We actually just sent chili peppers to ISS, and they'll be growing this summer. And we're really excited about peppers because they're very challenging. They take a long time to germinate. They take a long time to grow, about 120 days. And there's a real challenge with the flavor of the fruit. If we were to overwater them, they would taste like grass clippings. If we underwater and we stress them out a lot, they're gonna get real spicy. So we're trying to really control for growing healthy plants and flavorful plants with the correct you want us to eat and enjoy.
Right. And you know what they say, if you can't take the heat, get off the space station, right? Just kidding, that's my dad joke of the day. Anyways, well, Matt, I can't thank you enough for being here. I learned a lot, and I hope you all did as well, and I can't wait to hear what you grow in space next.
Thank you, Kathleen.
Shut your little door, Bowie. I can't hear.
Nope, Lucy. Still a little way to go before you get to your first Trojan asteroid. But it looks like you're coming up to the main belt asteroid, Donald Johanson. Right, this'll give you a chance to check in on your instrumentation before you get out to the Trojans. This first instrument is called LaRalph. It will take color images of the Trojan asteroids using visible and infrared light, helping scientists map craters and mountains and figure out what the asteroids are made out of. Next, this is LLORI, the Long-Range Reconnaissance Imager. This camera will provide the most detailed images of the surfaces of the Trojan asteroids to help scientists figure out what's been happening since our solar system formed. This is LATES, the Thermal Emission Spectrometer. Basically a touchless thermometer. It will measure the temperatures on the Trojan asteroid's surfaces to tell scientists whether the surfaces are rocky or dusty. Lastly, you couldn't get the job done without your tracking cameras or the T2 cams to make sure the asteroids are always in view. And the high-gain antenna that lets you communicate with Earth. The scientists back at home will use your radio signals to measure the mass of each asteroid as you fly past it. Right, Lucy, how could I forget? You also have 2 huge solar panels to give you electrical power as you fly out to the Trojan asteroids. Farther from the sun than any previous solar-powered mission. Just a bit longer now before you get to your first target. Rest up and get ready to put all of those instruments to good use. I'll check back in with you once you make it out to your first Trojan asteroid.
Hi, my name is Paul Morris, and I'm a video producer for the Hubble Space Telescope. Over the years, I've had the amazing opportunity to interview some of the brightest minds in astrophysics and some of the coolest astronauts and people in the world. As a rule, I always ask every single person this one question, every single time.
This is the cliche question.
Always
What
good.
is your favorite Hubble image?
Oh, whoa, what is my favorite Hubble image?
Can you talk about your favorite Hubble image? What is your favorite Hubble image and why? What is your favorite Hubble image and why?
I began to see a pattern in their answers.
The Hubble Deep Field.
The ultra deep field.
The ultra deep field, one of the questions you were going to ask me was what was my favorite image. My favorite image is the deep field image. It's because it's one that tells an incredible story about our universe.
Back in 1994, Robert Williams, then director of the Space Telescope Science Institute in Baltimore, Maryland, came up with a plan. He wanted to point Hubble at a spot in the sky where there was seemingly nothing there. A lot of scientists and astronomers at the time thought this was a huge waste of valuable Hubble resources and pushed back. Williams, however, continued forward with his plan. He controlled 10% of Hubble's observation time, known as Director's Discretionary Time. He decided to use some of that to take a long exposure that would be made immediately available to the public. Taken over the course of 10 days in 1995, the Hubble Deep Field captured roughly 3,000 distant galaxies in various stages of evolution. 3,000 galaxies where it seemed like there was nothing. The world was stunned.
When we finally looked at what came back, it was one of the most mind-boggling images of the whole Hubble collection. Galaxies with billions of stars and billions of planets we know nowadays, and guess what? One of those planets in this image may have somebody like you or me, or some other intelligent life form that we don't even know about yet, so we gotta keep searching. We gotta tell that story, you know.
The deep in Hubble Deep Field refers to the telescope's ability to look at some of these far, faint objects. Looking at faraway objects in space is like seeing back in time. Light moves at tremendous speeds, but it still takes time to travel across the vastness of space. Even the light from our own sun needs 8 minutes and 20 seconds to reach Earth. So when we look at the sun, we see it as it was a little more than 8 minutes earlier. The farther away the object, the younger it appears in Hubble's eyes. The deep field was like a core sample of space, showing galaxies at different and earlier stages of development, the deeper they appeared in the image. Science and astronomy is all about honing and improving our senses. No one expected the Hubble Deep Field to have thousands of galaxies in that single image.
We thought X, and we were so wrong. And that experiment, it took great engineering to do with a great system, Hubble, allowed the astrophysicists to say, hold it, you know, it's different. It helped connect the dark energy, dark matter theories to what the light we can see is. And for me, it's beautiful because it's like looking into a pond and seeing the water molecules and the living cells that are micron around of the microbes. It's like that kind of moment. It must have been like the early microscopists who first looked at pond scum and said, oh geez, there's stuff going on. Or Galileo when he first sensed the satellites of Jupiter.
Since the original Hubble Deep Field, Hubble has gone on to collect over 20 deep fields of various parts of the sky in multiple wavelengths of light. To create each image, it has gazed at the same point in space for many orbits, gathering as much light as it can. Every single one of these increased our knowledge of the universe and our place in it. The Hubble Ultra Deep Field, for instance, released in 2004, had a longer exposure time than the previous deep field. This new snapshot contained even more galaxies of various ages, sizes, shapes, and colors. The smallest, reddest galaxies may be among the most distant known, existing when the universe was just 800 million years old.
When I stare at that image, my imagination goes wild. I wonder what it would be like to visit any one of those little smudges of light, which would be presumably possibly similar to our own Milky Way galaxy. And also realizing that if we extrapolate that image to the whole sky, that's what our universe looks like. In any direction, we see a collection of galaxies like that.
The width of the Hubble Ultra Deep Field is less than 1/10 the diameter of the full moon. That's like looking through the eye of a needle held at arm's length. And in that tiny space, we found 10,000 galaxies.
10,000 galaxies in that single space. 10,000 galaxies in that one too. 10,000 galaxies there and 10,000 galaxies there. 10,000 galaxies there and 10,000 galaxies there too. If you add them all up, that means the entire observable universe is estimated to contain at least 200 billion galaxies. 200 billion galaxies. If each galaxy has an average of 100 million stars in it, then that means there are at least 20 quintillion stars in the observable universe. That's a 2 with 19 zeros after it.
It makes me, of course, just overwhelmed, but also just very curious about, wouldn't it be wonderful if I could just beam myself over to one of those galaxies and explore around and see if they have stars and planets like we have in our own Milky Way, and just be amazed, not only at the magnitude of the universe, but to be grateful that I can be a part of the universe and have the ability to look out and see this grandeur. That's what I love about the ultra deep field, and that's what I love about astronomy images in general.
The death of an island is a common occurrence on our Earth, and today, ISAT-2, our satellite LiDAR altimetry system, can see and watch these spectacular places. It's almost spooky, because islands are part of the glimmers of how the Earth works in the giant oceanic environment. So let's take a look at one of these island systems in a remote part of the Southwest Pacific known as the Kingdom of Tonga. And this island archipelago is special because it has lots of volcanoes. Recently, ISAT-2 was able to produce topography of one of these islands, a recently formed one known as Hongatonga Hungahapai in the Southwest Pacific. And this island, only a couple hundred hectares in extent, was burst from the shallow waters, oceans of this part of the Pacific about 6 years ago. It constructed a 120-meter high volcano, and that volcanic island has been crumbling against the barrage of forces of the ocean and tropical cyclones over the last 6 years. ISAT-2 was able to see that island with the finest scale precision of satellite laser altimetry possible and show us the structure of the island as it's crumbling. And what ISAT-2 shows us is the shallow crater lake that formed as the volcano was erupting and then filled with ocean water is only 10 or 15 meters deep. It reflects what might be the volcanic vent system that led to the formation of this special island. Now, other islands in the Tonga system haven't survived as well. And one erupted beautifully in the fall of 2019. And that island, which is named Lateiki, formed a new island just several meters above sea level that was then witnessed by ISAT-2 a few months after that island washed away. And what's left are the remnant shoals of a region that's very active, the tip of a 3-kilometer, 10,000-foot undersea volcano that pops its head above and below the waves every decade or two. The death of islands is like the ghost-like relics of what the Earth once was. And we know there's thousands of these things on the ocean and the seafloor, most of which don't poke their heads above the water.
For 2022's Black Holes Week, NASA wanted to create a data-driven visualization of a new database of black holes that have been observed co-orbiting and feeding upon their stellar companions. Tabulated data was provided by Dr. Jeremy Schnittman, which represented many geometric characteristics of these black hole systems, like the black hole mass, the star mass, the space between them, and their shared orbital period. Inspired by Dr. Dan Fabrici's Kepler exoplanet orrery, NASA's Scientific Visualization Studio set out to create an orrery of Dr. Schnittman's 22 black hole systems. By applying the database attributes to simple geometry, and by inferring other characteristics through physical equations and informed estimates, they were able to use advanced Hollywood visual effects tools to bring each black hole system to life. Arranging them in an optimal shape proved difficult, with early attempts including a 3D spiral and even clockwork gadgetry. But the most decipherable layout proved to be a series of concentric rings, with the largest black hole system, GRS 1915, at the center. When communicating with data, it is often more important to make something understandable than it is to make it photographically real. In reality, all of the black hole event horizon dots at the center of each accretion disk would be smaller than a single image pixel. But for this sequence, they are sized proportionally to their mass to make it clear that they are indeed black holes. Their minuscule sizes were also the reason no gravitational lensing is apparent. Orbit lines were added later to illustrate the sometimes surprising gravitational influence each of these massive objects has on its companion. The gravitational warping of each star and the differential rotation speed of each accretion disk was mathematically derived from the source data. Each accretion disk was comprised of 2,000 textured particles. It took almost 3 weeks running across the studio's 100 render farm machines to generate the final videos of the orrery and each black hole system in close-up, generating 27,000 4K final image frames. There are likely many more black holes with companion stars yet to be observed, and we look forward to seeing this dataset and visualization grow and evolve over time.
Features in Earth's atmosphere, spawned by the heat of the sun and the rotation of the Earth, transport water and energy around the globe. Clouds and precipitation shown here are from NASA's MERA-2 reanalysis, a retrospective blend of a weather model and conventional and satellite observations. Within the mid-latitudes, winds move clouds from west to east. Within the tropics, easterly trade winds converge along the equator to create a moisture-rich cluster of clouds, convection, and precipitation called the Intertropical Convergence Zone, or ITCZ. Disturbances in its flow transport immense amounts of moisture and energy from the tropics to the poles. Studies have shown that atmospheric rivers account for the vast majority of the poleward transport of water vapor. The American Meteorological Society defines an atmospheric river as a long, narrow, and transient corridor of strong, horizontal water vapor transport that is typically associated with a low-level jet stream ahead of the cold front of an extratropical cyclone. A common measure for the strength of an atmospheric river is the integrated water vapor transport, or the amount of moisture that is moved from one place to another by the flow of the atmosphere. The blue shading shown here gives a three-dimensional view of the water vapor transport. Tropical moisture is pulled in from the ITCZ, and in this example, converges with other flows to form an atmospheric river. The feature then travels toward the west coast of the United States as a subclass of atmospheric rivers commonly referred to as the Pineapple Express due to its origin near Hawaii. The atmospheric river is guided by the semi-permanent subtropical high pressure off the coast of California and the Baja Peninsula, as well as the Aleutian Low in the Gulf of Alaska. The pressure gradient between the clockwise flow of the Californian high and the counterclockwise flow of the Aleutian Low funnel the atmospheric moisture into a narrow corridor. The more intense the pressure gradient is, the stronger the winds are that transport the water vapor. Extreme rainfall has also been associated with the more intense gradients. Much of the moisture stays close to the surface, but the rising motion of the low pressure to the north results in the air cooling, condensing the water vapor into a liquid. Precipitation over the ocean falls along the feature's cold front on its northern side. Another way that air can rise and condense into precipitation is through orographic lift. When air encounters the mountains along the west coast of the United States, it is forced upwards. The rising air becomes saturated, causing rain and snow to fall, particularly on the windward side of the mountain. The flow of air continues eastward, depleted of its moisture. The precipitation that falls because of atmospheric rivers is important for the hydrologic cycle in the western United States. The winter buildup of the snowpack provides valuable freshwater resources. Despite being beneficial at times, atmospheric river-induced precipitation can also be destructive. The occurrence of extreme atmospheric river precipitation events, such as the one that occurred in this example, can result in widespread flooding and mudslides. Atmospheric rivers are not unique to the west coast of North America and occur around the globe, including New Zealand, Greenland, Antarctica, and the Middle East. The study of global phenomena such as atmospheric rivers over the past 4 decades is made possible through NASA's MERA-2 reanalysis, a spatially and temporally consistent blend of satellite and conventional observations with a numerical model. With a data set that provides hourly information around the globe since 1980, there's still much that can be learned about Earth's atmosphere and the transport of water and energy around the globe.
It's thrilling to be able to see something that's never been seen before. This emission that we're seeing is thermal emission. Even on the night side, the surface of Venus is so hot that it's glowing faintly at very red wavelengths.
These whisper images, I think, are really exciting because they provide a new window into the lower atmosphere and surface region of Venus where these extreme conditions exist. Another really interesting thing we could look for is potentially mineralogical differences. Different rocks and different minerals emit different levels of heat. We have chemical fingerprints in Venus's atmosphere and on its surface, suggesting that Venus might have been habitable in the past.
That's truly new, and I believe will yield exciting science in the long term.
A little slower. And it all comes down to this. This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1,000,000 miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time, almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4-meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
6, 5, 4.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you, shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our high-gain antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1,000,000 miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet, then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers, or approximately 8,900 square feet, almost the size of 3 tennis courts, a very thin Kapton material, about 1 to 2/1000ths of an inch thick. Making them go where you want them to go in 0G is extremely challenging.
The sun shield shades the telescope from the heat of the sun, Earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sunshield under control as it unfolds. First, we release these special restraints that protect the sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy aside. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sunshield release mechanisms need to fire on cue. 107. They free the 5 sunshield layers, allowing them to extend as the mid-booms deploy.
Sunshield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, the secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos,